Hello everyone, my name is Ingkarat Rak-amnouykit. Today, I am presenting the paper Python 3 Types in the Wild, a tale of two type systems. This paper reviews the semantic of MyPy and PyType and contrasts the two type systems. We present a study of Python 3 type uses by developers. Then, we did a large-scale empirical study of MyPy and PyType on a corpus of public GitHub repositories. The motivation is to improve understanding of Python types and tools, with the ultimate goal of reducing Python errors in the wild. Python 3 is a dynamic language. PEP 484 introduces a syntax for expressing types, creating a standard type annotation syntax for static analysis. This example shows type annotations for a function parameter and a return type. We study two popular tools, MyPy and PyType, which approach type checking differently. MyPy behaves like a conventional static type system in a sense that it does not allow variables that change type. PyType conforms more to legal Python usage, where types can change in the function. It allows variables that change type if operations succeed at runtime and do not contradict annotation. Let's start by looking at the type of an unannotated local variable. We reassign x to another type. MyPy flagged this as an error. PyType, however, allows this and infer x to be type string afterward. Next example is a type of an unannotated function parameter. Surprisingly, MyPy type checked this code. This is because MyPy maps untyped parameter to any, so x has type any throughout the function. PyType does the same thing as in previous example and infer x at the end to be of type string, which contradicts the annotated return type of integer. This example shows type of list and dictionary literals. We create a list x of mixed types of string and integer, then pass it to function f, whose argument is annotated to be the union of integer and string. At line 4, MyPy infer type of x to be a list of objects, which is incompatible with the type of parameter p. PyType, on the other hand, infers x to be a list of union of integer and string. For this last example, we have both annotated and unannotated functions. MyPy does not type check unannotated functions and infer the return type of them to be any. PyType infers that this unannotated function returns an integer, which conflicts the annotated return type of the second function. In the remainder of the talk, we will address the following three research questions. First, how often and in what ways do developers use types? Second, which type errors do developers make? And third, how do type errors from different tools compare? First, we look at how the developers use types. We examined a collection of 70,000 Python repositories from public GitHub. 2,678 repositories have at least one type annotation in at least one file. Of these, only 318 repositories pass MyPy. Why are so few repositories type correct? One hypothesis is that MyPy may be too conservative. It produces false positive warnings more than actual runtime errors, which might discourage developers from fixing types errors. Still, developers see value in writing type annotations as they serve as documentation. Another hypothesis is that MyPy might not be a tool of choice. Developers might prefer other tools that are more lenient or ones that are more readily available in popular IDEs. We look at the frequency of type categories used across the 2,678 type repositories. Note that the graph is in log scale. The highest frequency is types in the user-defined categories. It includes user-defined classes, classes defined in built-in Python modules, and third-party modules, as well as type variables and type areas. User-defined types are hard to further break down into their subcategories because that would require more sophisticated analysis. In repositories that we examined, we found that developers often use non-local user-defined types as a type connotations. We conjecture that this is to improve documentation and readability in the code. Next highest frequencies are simple types, string, integer, and boolean. None and optional are also prominent annotations. Next, we look at which type errors do developers make. Both MyPy and PyType have their own error codes. The graph shows the error code distribution of MyPy in log scale. We classify them into 4 categories. First is deep semantic errors, which are standard type errors. For MyPy, examples are assignment errors and return value errors. Next is shallow semantic errors, which require less sophisticated semantic analysis. For example, MyPy call argument code checks the number and names of arguments at function calls. The remaining 2 categories are syntax errors and import or author errors. Next, we sample 15 error codes for each of the most common error codes and hand inspect them. The table shows the summary of 105 MyPy errors and 77 PyType errors. 49% of MyPy and 44% of PyType are false positive according to our inspection. For MyPy, it's mostly due to the redefinition of variables and the use of optional types with non-check. PyType has different semantics, so it won't flag many of MyPy false positive. Lastly, most incorrect annotations were found in MyPy return value code and the PyType bad return type code. Lastly, we want to know how do type errors from different tools compare. We are interested in errors reported by MyPy and PyType on the same line of code. Excluding import-related errors, MyPy reports 23,665 errors, and PyType reports 65,938 errors. The difference in numbers is largely because MyPy does not type check unannotated functions. Overall, there are some overlap in deep semantic errors, but little overlap in shallow semantic errors. These figures show a comparison between MyPy and PyType errors that appear on the same line. The left figure is a matching from MyPy's deep semantic errors to PyType errors. The right figure is a matching from PyType deep semantic errors to MyPy errors. We will be focusing on the left figure. We will look at 4 of MyPy deep semantic error code. First, there is a strong connection between MyPy's return value code and PyType bad return type code. They roughly check the same thing. The main difference in number is due to MyPy not checking an annotated function. For MyPy's operator code, there is small overlap with PyType's unsupported operands code. This is due to differences in the inference semantics. For example, the following code passes PyType, while it gets flagged by MyPy assignment and operator errors. PyType unsupported operands also checks if the variable type supports indexing, which maps to another MyPy's code called index. Regarding argument types, there is overlap between errors reported from both tools. For MyPy's argument type code and PyType wrong argument type code, they both detect argument types that are incompatible with the corresponding formal parameter type. There are some MyPy codes that do not have corresponding PyType codes. For example, MyPy's variable annotated is reported when an empty list or dictionary is initiated without type annotation. Conclusion. First, we found that most open source projects do not yet use Python 3 types. Those that do use types are rarely type checked. Next, it seems like developers rarely type check their code. MyPy may be too conservative and produce false positive warnings more often than catching actual runtime errors. PyType behaves more like a static analysis tool, but also produce false positive warnings as well. Developers may ignore warnings and use annotation as documentation only. Nevertheless, type checking is still useful. On the one hand, types catch bugs such as in the use of optional types that may be none and in function return type annotations. On the other hand, the tools frequently disagree with user annotations and with each other. Lastly, MyPy and PyType are two different type systems with different semantics. This affects when and where errors get detected. With apologies to Dickens, it was the best of types. It was the worst of types. Thank you.